again late in the next week. So let's continue in the matrix calculus. And I was thinking about what would be a nice and reasonable example of application of these kind of strange things, or perhaps looking strange but not strange, in data science. And of course the first thing which comes into question is the discussion how to choose the right projections from high dimensional data from much lower dimensional data in a way which loses as little information as possible. And that's what's called principal component analysis. So you can imagine, so you have just in R, well, if you would draw it as a picture, so we would have, say, in R3, of course, in real data problems, so you would have something like not R3, but R many thousands parameters measured or collected somewhere, and there you have a lot of values, and say instead of 3 dimensions, you want to find a 2-dimensional subspace or some other subspace, so say that would be something like, say a 2-dimensional plane where you project all the things, so you get a projection of the bunch of data, and you would like to recognize the similarities and differences as good as possible even after the projection as before. So what shall we be doing, right? So it's actually not difficult, so let me choose another color. I don't like so let's go for yellow. So we have got some n collected components of data, right? So you see P is the number of the data, of the components of the individual data, and you have a collection of n of such, right? So you can imagine that you measure something like 37 parameters of some configuration, and you have it for 100,000 samples, and you want to categorize them and split them into some groups or work with them, and of course 37 could be too big, so you want to project it to some smaller place. And so what you can imagine is you take the means of the individual components in your data, so for each of the vectors, so this 37 component long one, you just take the mean of them. A mean is just the arithmetic mean for us here, why not? And then you look what is the amount of information collected in the data, right? So what's the variability of the data? If all the vectors would be exactly the same, that of course you wouldn't need to have so many of them, so the n, right? And it would be enough to have just one. But if you have many of them, then perhaps there will be some information hidden there, and the amount of the differences is reflecting or related to the amount of information there, and the sample variance is the parameter which tells you, and it's actually the sort of Euclidean distance of the individual components from the mean, right? So it's just for each of the components. So now I'm watching it the other way around, right? So if I would put all the vectors into rows of a matrix, so now I am looking at the columns, so the individual components of the vectors, and for each of them I have a mean, and I look how far I am from the mean. So this is something like the Euclidean square of the norm, and it's just divided by n minus 1 just to normalize it, and there is some good reason you will understand some, say 3 or 4 semesters later, why not 1 over n. This is a little bit better from expectation point of view. So that's the sample variance, and now you get the vector of means. So you see for each of the component you have the mean, you have the sample variances, and then you can of course compute the sample covariance matrix. So the i's vector difference from the mean taken once as a row and once as a column, and putting them together will give you a matrix, right? So this is a column and this is a row, so column times row, so it's a column times row. So all together it will, as a matrix multiplication, provide a matrix. And the matrix is the so-called sample covariant matrix. And by the very construction you see that it's of the form which we saw in the last week in my presentations or when reading the text. So you clearly have a symmetric matrix of reals here. And all the reals are non-negative, so it's something nice. So we know that all its eigenvalues will be real. All eigenvectors are pairwise orthogonal because it's representing a self-adjoint map in our abstract description. And how do we minimize the loss if we want to project, say, to k-dimensional subspace? We simply take the k of the biggest eigenvalues, so we start from the top, from the biggest one, and go through the k ones one by one, and we project orthogonally to the subspace which is spanned by the mutually orthogonal eigenvectors. And that's an orthogonal projection, and that will be the projection which minimizes the loss of information, and that's called a principal component analysis. And that's absolutely crucial method which you perhaps already met before as one of the toolboxes used in your work whenever you work on data. So that's, well, maybe I wanted to say at the end of the presentation, but let's have a look at an example here. So the next one is the example. So that's a very sort of simple-minded and stupid example, but say we are measuring and we want to distinguish between people whether they are big or small, and we shall be measuring three parameters. One is the length of the index finger, one is the length of the little finger, and one is the height of the person in centimeters. And then this is the collected numbers from a couple of people. And if you go through the procedure I described and you want to restrict everything to one parameter only, so you will project to one-dimensional subspace, right? So from 5 to 1. And you will see that to distinguish between so many, maybe you have hundreds of thousands of data then, but based on the three you train your decision making, and you find out that what comes as the principal component is very similar to the height. My fingers somehow do not do what I need, right? So the eigenvalues are of this kind, so I take the biggest one, I take the eigenvector, and I get the principal component, the first one. And so if I use this projection for any other data later, then I might believe that it will be sort of the best ever one-dimensional approximation for the decision-making purposes. So, thanks, that's it.